So what we just figured out, one of the things we just figured out, is that if we start with a matrix A and we switch two of its rows to get a matrix B, we figured out what that does to the determinants. What we found is that switching the rows also switching any two rows switches the sign of the determinant. So it puts an extra minus sign in front of the determinant. Well, switching two rows, that was an elementary row operation. What we should do is figure out what the other elementary row operations do to the determinant. So let's start with multiplying a row by a scalar. So let's suppose we start with a matrix A, we multiply its ith row by a scalar, say k, to get a new matrix B. How will these determinants compare? So let's find the determinant of B. Now we know we can expand this determinant across any row, and it seems like we should expand it across the ith row because that's where A and B are different. So let's expand across the ith row. We get the sum from j equals 1 to n of bij times the cofactor of b when we've deleted row I and column j. Okay, but how do these things compare to A? Well, bij, right, this is in the ith row of B, but the ith row of B is the same as the ith row of A, it's just been multiplied by k. So bij is actually k times aij. And then what about the cofactor? Well, all of the entries that make up this the determinant hiding inside of this cofactor, all of them are away from row j, right? Away from row I. Away from row I, A and B are actually exactly the same. So the ij cofactor of B is actually exactly the same as the ij cofactor of A. But now we can move this k outside, k times the sum from j equals 1 to n of aij times the ij cofactor of A, but that's k times the determinant of A. So if we multiply a row of A by a scalar, that multiplies the determinant by exactly the same scalar. All right, so 2 down, we've taken care of switching rows, which was very difficult. We've taken care of multiplying a row by a constant, which was actually surprisingly straightforward. The last one is adding a multiple of a row to another row. So let's suppose that we add a multiple of row I to row k. So how do the matrices compare? So what we're going to do is, okay, we start with A, and we will take row k plus some constant times row I. So this is how we're going to do it, and that gives us B. So remember, the matrices A and B are the same except in row k. Right? Row k is the only one that's changed because that's the one that we've added a multiple to. Let's find the determinant of B. So what row should we expand this determinant along? Well, expand along the row where it's different from A. So this is the sum from j equals 1 to n. We're going to expand along row k, so bkj, times the cofactor of B in position kj. All right, so this is sum from j equals 1 to n. So bkj, well, this is in the kth row. And what is the kth row of B? Well, it's the kth row of A plus C times the ith row of A. So bkj is actually akj plus C times aij. All right, so that times the cofactor of, well, what about the cofactor? Well, for this cofactor, we've deleted row k. But row k is the only place where these two matrices were different. So this kj cofactor of B is the same as the kj cofactor of A. All right, so what should we do next? Well, I don't know, this plus here makes it seem like we ought to distribute the cofactor. So this gives us the sum from j equals 1 to n of A, K, J, cofactor of A, the kjth cofactor of A. So that's when we distribute here. When we distribute to this CAIJ term, we get plus the sum from j equals 1 to n of CAIJ cofactor of AKJ. Now we can move this outside here. Okay. Yes. And this first piece, this is just the determinant of A. Plus C times. Now here we have to be really careful because the cofactor, we expanded across the kth, kth row, right? That's why there's a k here. But in these entries, it's not entries coming from the kth row, it's entries coming from the ith row. So this is the determinant of A, but the kth row has been replaced by the ith row. Right? For this expression, we didn't add a copy of the ith row to the kth row. We actually just replaced the kth row with the ith row, right? Because it's just a sub ij instead of a sub kj. So what happens to a determinant if you have the same row in two places, right? Here, this matrix here, that we have the cofactors of, or that we have the determinant of, it looks exactly like A, right? It has the first row of A and so on. It has all the rows of A, except in the kth row, instead of the kth row of A, it's actually the ith row a second time. So our matrix looks like this. What does that do to the determinant? Well, remember, the determinant is defined inductively. So we can choose to expand our determinants so that these two rows where the AIs show up, so these show up, these get eliminated last. Okay, so as we expand our determinant to smaller and smaller sizes, eventually we're going to get determinants coming from only these two rows, right? So, right, we'll have AI1 and AI2, for example, and then AI1, AI2, right? Every determinant that comes from these two rows will have two different column positions, but the same row position because these two rows are the same. Well, what happens if you get a 2 by 2 determinant like this? This 2 by 2 determinant is 0. You can just calculate it. You get 0. So because there's a repeated row, when we expand the determinant all the way down to 2 by 2 determinants, we get nothing but zeros. But that means that this entire determinant is 0. So the result of this giant calculation is that we just get the determinant of A. Right? And what we started with was the determinant of B. So what we found is if you add a multiple of a row to another row, that does not change the determinant at all. And that's a little surprising. All right, so now we know what the three elementary row operations do to determinants. If you switch two rows, it multiplies the determinant by -1. If you multiply a row by a constant, the determinant gets multiplied by that constant. And if you add a multiple of a row to another row, that doesn't change the determinant at all. All right, so that's the row operations. But remember, the row operations correspond to elementary matrices, which makes you wonder, what are the determinants of the elementary matrices? So what about row interchange matrices? Well, row interchange matrices, they all look like the identity, but with two rows switched. So the determinant of one of these is the same as the determinant of the identity, but since we switched a row, it has a minus sign. But the identity is a diagonal matrix. So the determinant of the identity is the product of the diagonal entries, which is 1, since all the diagonal entries in the identity are 1. So this is just minus 1. So the row interchange matrices, they all have a determinant of minus 1. Okay, what about multiplying a row by a scalar? So the elementary matrix for multiplying a row by, say the scalar is C. The elementary row operation for multiplying a row by a scalar is just to have a C in the row that you want to multiply by C. As usual, any entries that I am not writing down are zeros. What's the determinant of this? Well, this matrix is also triangular, it's diagonal, so its determinant is just the product of the diagonal entries, and they're all 1s except for this one, which is a C, so we just get C. Finally, adding a multiple of a row to another row. Remember, the elementary matrix that does that is all 1s down the diagonal, but then somewhere off the diagonal, either above or below the diagonal, but not both, there is a scalar somewhere. So there's some scalar down here. But look, whether this C shows up below the diagonal or above it, the opposite side is just full of zeros. So the determinant of this matrix is just the product of the diagonal entries, which is 1. So now we know the determinant of all the elementary matrices, and we also know the effect of row operations on the determinant. It turns out that putting these two together will give us some amazing properties of the determinant.